All right. Everyone hear me okay, especially at the back? All right. And just to say, I really appreciate everyone wearing masks. I just happen to be high risk, so if you can wear a mask, it's much appreciated. All right. So, topic of this lecture is going to be LHC experiments. And given the school I'm at, has anybody actually done any experimental particle physics? Yes, a handful. Okay. I'm not aiming it at you guys. I'm aiming it at everybody else, but I just wanted to see what they are. And here's kind of an outline of the topics I'd like to cover. Sort of for most of today, I'm going to start right at the beginning, which is how we actually go about making the various physical processes. So tell you a bit about accelerators. Then I'm going to tell you how we actually detect them. So various different detectors. These are going to include tracking, we're going to talk about calorimeters. These are kind of the two big workhorse types of detectors that we have. Talk about a few other smaller ones, and then sort of put it all together into the experiments we have at the LHC. Then assuming we don't get into too much discussion, but I like discussion, so questions are super welcome, I will give you some examples of how we actually put this all together into doing analysis and sort of getting back to some of those plots that you've been seeing from the various different speakers to do it. So that's a brief outline of the topics. Did I just lose something? No. Okay. All right. So let's get started. Okay. So as I was saying, actually that's not going to be big enough. Let's do this again. We're going to start by talking about accelerators. And there are many different types of accelerators you can think about. You can think about colliders. You can think about fixed target. You can also think about neutrinos. And the reason that I mention this, right, is this is one of the two ways that you can think about creating the physics process that you're interested in. So overall, that's what we're interested in. We're interested in creation of the physical process. However, that's not the only way to do it, right? Sometimes we're lucky, right? Sometimes we can actually use nature itself to make the physical process. Sometimes we don't have to build some gigantic machine, use tons of electricity, etc. And so the second way we can think about doing it is we can use natural processes. And there are actually tons of different ways you can do this. You can have cosmic rays. Some of the earliest ways that people were studying particles. You can think about nuclear reactors. Byproducts, they tend to produce tons of neutrinos. And there are other spontaneous processes. For example, when some particle might decay. So this is the one hand, right? This is thinking, there's some physical process. I have to actually make that happen. Either I build an accelerator to do it, or it happens naturally. Advantage, if you think about it for an accelerator, is we can control quite precisely what we're doing, right? We can decide we want to use a specific particle. We want to do it at a specific energy. Whereas the natural processes, they just happen, right? On the other hand, we don't have to put energy in there. So if you want to get to super high energies, cosmic rays can actually make life much easier. And then the second part here will be the particle detectors. And here what we're after is we want to record and we want to reconstruct the physical processes. Of course, what will actually happen, right, is many of the physical processes that we're interested in happen very quickly, and the particles decay. And so it's often not the case, right? I don't build a Higgs boson detector. That would make my life really easy. Often what you actually need to do is we need to reconstruct the decay products from whatever particle and then figure out what originally happened. And so it's a little bit more complicated than, seeing the actual particle that was produced. So the basic idea of particle accelerators is that we're after doing physics at high energy. Why do we care about high energy? Typically, that's because we're after trying to find some sort of new physics or new phenomena. And often, these are predicted to occur at higher energies. And so generally, what we want to do is to get to as high energy as possible. Not the only thing we want to do, but that's sort of the primary way of thinking about it. And there are kind of three strategies. So strategy number one, which is the one you kind of think about when you start thinking about this, is that we want to create particles. Notice I use the word create here. What we mean by that, right, is we're trying to create different particles, not the ones that I stick inside my accelerator, create some sort of new particle through high energy collisions. And here we're taking advantage of one of the simplest formulas, the one that people who tend to not study physics actually will talk about, which is simply E equals mc squared. And that's why we're after high energy. We want to get to as high a mass as we possibly can for these particles. Examples of these, and we'll come back to this a little bit later, could be an E plus E minus collider, or something like the LHC, which is a hadron collider. Okay, so that's strategy number one, right? Energy, making new particles in mass. Strategy number two would be we want to keep the particles that we have, but we want to scatter them and these can come from a beam or not. Depends what you're after. And we would do this via some sort of target. By target, I really mean some chunk of typically heavy material that we would have. Now, why would we want to do this? Various different reasons. For example, actually that target might be the thing we're interested in. If that's the case, we might be wanting to study the structure of the target. A classical example here would be something like Rutherford scattering. Or maybe we're interested about the interaction of the beam and the target. So we might want to understand interaction between the beam and the target. Examples of this, for example, would be, let's say we would like to understand the weak neutral current. This is how it was done. And we did this via neutrino proton scattering. There are other ways you could do it. For example, you might be trying to find dark matter, right? So in that case, we might want to confirm the existence of the incoming particle. So we have a detector. We want to see that interaction in the detector. So we might also be looking for dark matter. Let me just flip these over. No, I'll go on to the next one. All right. Actually, let's make sure you can see this. All right. Number 3 that we could have would be to directly measure. So here the keyword is measure. A particle's properties. And so here you're really trying to see a direct interaction with the experimental setup. Examples of these, maybe we're interested in measuring a decay rate. And a sort of classical example that you could think about today would be to confirm detailed standard model predictions. And the kind of hot example of that right now would be the muon magnetic moment. So you can see here that if you think about it, we're using the same basic technique, right? We make a beam of particles, we either clash them together, or we hit some target. But we're often using this in very different ways, depending on the physics topic that we're interested in. Yeah, question?
Why was the LHC chosen to be a hadron collider? Because you could have made the Higgs lots of ways, right?
So I'm going to come back to that a little bit later, but I'll give you a brief answer. Typically in particle physics, we kind of alternate. We go from electron-positron machine to a hadron collider, vice versa. And the reason is with hadrons, you can get to higher energy. And so if you're primarily after finding new things, this is the quickest way to do it. Whereas E plus E minus is a lot cleaner. And so you do that afterwards to do it. So it's not entirely true that the LHC was built to find the Higgs. It was one of the things we knew we found. But in fact, if you ask people sort of what their motivation was, their primary motivation, I would say most people were after finding new physics, with knowing that we had to say something about the Higgs either way. So that's kind of why. If we were just finding the Higgs, and we knew its mass, then let's build an E plus E minus collider at that mass. But at the time, we didn't know at all, basically. Sure. Actually, we'll get there. Coming to that soon. Yeah, another question.
Are you going to talk to us a little bit about any other no-lose theorems that we might have?
No. That's not going to fit in my lecture to do it, but indeed, that's a lot of what people are thinking about, right, in the context of saying, what should be the next collider that we could build. And there's some which are partial no-Lewis theorems that people have come up with. I would definitely say there's none that are as strong as the argument we had for the Higgs. But we can chat about that after. Unfortunately, it didn't fit quite in this lecture. So that's kind of why. Now let's get on to a little bit of the details of how we actually would build an accelerator. Gosh, these don't really clean very well. Hopefully you guys can still read it. And so what I want to talk about next are the different components of an accelerator. Again, here they're going to be three. Number one, you need a beam. And a beam and an accelerator, one way to think about this is that it's actually a current of charged particles. Anyone know why the particles need to be charged, primarily? Exactly, that's going to be point number 2. We're going to need to be able to control this beam. And for now, our primary method is essentially electromagnetism. And so we need to have charge to be able to do that. Now, inside an accelerator, it's not the case like in the LHC, there's just one proton. And we put another proton and we collide them together. We could do that. But if we did it, it would take absolutely ages before anything would happen. So what we actually have is we have bunches. That kind of means what it says. It means we have a whole bunch of different particles all together. And to give you a feeling for this, in the LHC, it's something like 10 to the 11 protons per bunch. So actually tons of protons per bunch. And the reason for that is that we want to increase the probability of something happening each time our protons collide. You can think about, the cross-section size is super tiny. This really increases the chance. It is also the primary source of many of the headaches of the work that I do, because unfortunately, while we make a very good chance of something happening, we in a sense do too well. And in fact, in the LHC, we get something like average 40 pairs colliding every single time. And so that's something known as pileup. So there's one interesting collision, might make a top quark or a Higgs boson, whole bunch of these other less interesting collisions, but we still have to deal with them. And we need to transport these beams in an ultra-high vacuum. Why do we need a vacuum here? The problem is that air itself, right, is made up of molecules, right? There are plenty of particles going by. And when you're thinking about those tiny little protons flying around, if they hit something else, that's going to deflect your beam or cause additional collisions. And so actually, each time we need to use the accelerator, we actually have to pump it down to this ultra-high vacuum to avoid all this messing up our beams. In fact, sometimes from time to time, we have trouble with this. For example, like I think a couple years back, there was some dust inside the beam pipe. And these became known as UFOs. Yes, particle physicists have weird sense of humor sometimes to do it, because they were indeed unidentified flying objects in the beam, messing it up. And so they had to develop procedures to really, clean this up, because this was actually messing up the quality of the beam. And so a vacuum is really important to have. Number two, just having a beam, pretty boring. Just got a bunch of particles hanging out. Next thing I need to do is I'm going to need to make my beam go to high energy. And so for this, I need accelerating structures. Typically, depends a little bit on your configuration. These are going to be either electric fields or most commonly, especially in accelerators that go to very high energies, radio frequency waves. That's not the only way you can do it. And in fact, there are many people working on new techniques. One of the ones that's pretty interesting and kind of cool is known as plasma Wakefield acceleration. I think this one is pretty cool for two reasons. So one, the name, this Wakefield, is actually pretty appropriate. The idea is that you can kind of try and get your particles to surf on the fields that you can produce. And so that's a nifty idea. But more importantly, it has the promise to be able to do much greater acceleration over much smaller distances. So if we could get plasma Wakefield acceleration to become something we could use, it has the possibility to make way smaller accelerators than we do today. And this would save us tons of time. Yeah?
Question about the first point. What's the difference in the electric fields and the radio frequency?
Of course, they're both electromagnetism. Just a little bit, sometimes you can just, for example, in like injectors and things like that, you'll just apply a straight up electric field. Whereas the other one, you'll actually have these cavities, right, which you pump with the waves, which will then accelerate. But of course, it's the same idea. And in fact, what you may be noticing is that in terms of fundamental physics properties that we rely on for accelerators, it's basically electromagnetism the whole way. This is how they actually work. But yeah, so these are usually, for example, in the injectors or the source, it can be as simple as just apply a field and move the particles. And then these are when you get to the bigger and higher energy accelerators to do it. And here you're really pumping in a field, and you get a sort of sinusoidal variation on it. Any other questions? Nope. Please shout at me if I miss questions. So that's number two, accelerating structures. Number three, which was already mentioned, we need magnets. And in some sense, magnets can sometimes be the most tricky part of building an accelerator. In the sense, this can limit your energy. And that is 100% true for the LHC. And we need magnets to be able to guide our beams in well-defined paths. We'll come to it a little bit later, but of course the LHC is a collider and a circular collider that we have. So in order to get your beam to actually go in a circle, you need to use magnets to bend it, to get the particles to do that. And that strength, right, how much we're able to bend those beams, that's what limits the energy of the LHC. That's why we haven't yet got 14 TeV. We should be getting 13.6 in a month or two, more or less, but so far it's been 13 that we've been doing. And secondly, they will focus beams to a small transverse area. If you think about it, right? Remember we talked about these bunches where we have a whole bunch of protons all stuck together? They're all charged. They're all repelling each other, right, all the time. And so naturally, if you just left your bunch of protons alone, they would kind of spread out to do it. On the other hand, if you want to collide them together, it's in your interest to really get them to as small an area as possible, because again, that's going to increase your rate of having collisions. And so that's where we need to use the magnets to do it. Yeah?
Instead of getting them all in a bunch, why not have a flat line in them, if that's even possible in some way?
So I believe that this is due to how we want to accelerate them to do it, one part of it. And the second part is if you had the flat line, you would decrease your chance of getting them to collide, right? Because they'd be distributed out from each other to do it. But secondly, I think it's also because of the acceleration, we pump it in at regular intervals such that it really gets the bunch itself to do it. I mean, this is kind of specific to that HC now, right? In other accelerator applications, you could most definitely have them in a line. It's a good question, actually. Thank you for the reminder. I need reminders. So the question was, why do we have the particles in a bunch? Why don't we just have a straight line of charge going throughout the accelerator? I will try and remember that. Sorry about that. Okay. So those are your kind of three components that we will have in an accelerator. And now we're going to get to the different types of accelerators. This will actually come back to one of the questions we had a bit earlier. Here again, I'm going to have three, but they're actually intertwined, and there's relationships between these different ones. Number one, we've talked about this a little bit. You can have a fixed target, or you can have a collider. And here, for example, the idea in a collider is that we have two beams colliding here. And with a little bit of work, well, not very much actually, you can calculate that their center of mass energy, which is going to be that energy relevant for E equals mc squared for making new particles, is simply going to be 4 energy of the first beam, energy of the second beam to do it. Most of the time, our colliders are symmetric in energy, i.e. beam 1 and beam 2 have the same energy. It doesn't have to be the case. Sometimes you want it to be asymmetric. And there's an example of a collider today that does that, which is Bell 2 in Japan. They're using highly asymmetric energies for a specific reason to produce Bs that they can detect in their detector. So it's a choice. Now, kind of one of the key advantages here is that in a collider, all the energy is available for hot scattering And here we use the term scattering when our particles don't get destroyed, and or creation of new particles. Type 2 here is going to be fixed target. And fixed target, the idea is we have our beam coming in, we have our target, something happens, and we create a whole bunch of particles. And here, if you do a bit of work and calculate the center mass energy, what you should find is this is 2 times mass of the target times the energy of the beam. So you can notice here, if you think about it, you're going to have, if you have beams of the same energy, and you use one in a fixed target experiment versus a collider, you're going to have much less energy available for the interaction. The other thing is that increasing the mass of your target here, you can actually increase the energy of the interaction. So that's typically why targets are very dense, so that you can increase it as much as possible. And so what that means is there is less energy for producing new particles. However, there is an advantage, right? And the advantage here is that we can really use a variety of targets and beams. We'll come back to it in a bit, but the type of particles that you use for the beam is very few. Yeah?
Are you saying that there can be more beam choices in a fixed target experiment than a collider experiment as well?
Depends, sometimes, because often what we do in a fixed target is you'll have a primary beam hitting a target, producing some other particle, which will be your secondary one, and then hit your target. This is a little bit if you know how the neutrino experiments are done, right? Because you can't accelerate neutrinos as neutral particles. So it's true, I said it slightly wrong to do, but it gives you a greater variety of interactions that you would be able to study in those cases. Yeah.
Does the mass of the target refers to the mass of the target nuclei, or?
It depends a little bit because obviously, right, your beam has a size, right? So it doesn't matter if you have this gigantic target and you're not hitting it. So it depends on the mass of the target that you manage to have in the interaction. So that's why I said density primarily, right? Because density would scale straightforwardly. Whereas you could also think about, having a larger beam size hitting more of the target, and then the size would also matter to do it.
I see. So here I'm not thinking about each of the particle-particle collision.
You're thinking about both.
Okay.
Yeah, so primarily you think about the particle-particle, and then in that case, really, we're thinking, like you were saying, of it. But you could also think about making it bigger if you want to. No, sorry, I'm wrong. I'm talking nonsense. Take that back. You're right. We're talking about the energy of the particle interaction. In that case, it's just the density of the nuclei that matters to do it. Sorry, you're right. Thanks. Other questions? Okay. Sorry, I forgot to repeat the question. The question here was about this formula that I just showed you, whether it was about the mass of the full target or it was the mass of the particle-particle collision to do it, and it's the latter. Let's actually do both of them. also quite squeaky. I don't know if you guys will hear that. For me, it gets very squeaky. All right. So I'm going to take a little bit of a pause here and talk about something which we're going to come back to in one of the later lectures because it's really important. And so this is in the context of colliders. If you want to think about the number of events that you'll produce, so that will be n event, this will be equal to sigma times L times delta T. Okay? Yeah.
Then this is not differentiating between signal and background, right?
No. Well, for now, I'm talking right now about, when I'm going to talk about luminosity. But if you're thinking about some particular signal process, then the sigma, the cross-section, you would use the cross-section of that particular process to do it.
So in the case of backgrounds, do we also maybe, I mean, I know we, like you said, we clean up our environment as much as possible, but I haven't heard, and I'm a bit curious about kind of external kind of sources that kind of impinge on our experiments, like we can't stop neutrinos and things like that sometimes.
So the question here is about backgrounds, right? So when we're doing a search, right, there's some particle we want to study. And it would be great if we could just study that particle. That's pretty rare. The question was, what about all the different backgrounds? There are actually many different types, okay? And this formula that I'm showing here, where we have the number of events equals sigma luminosity times delta T, that would apply to all physics backgrounds, right? And indeed, those are actually our worst backgrounds. So most of the time, they're things like soft interactions. These happen at a far greater rate than any of our interesting ones. There can also be, other processes which have similar decay signature, also a big background. But you're right, there are other backgrounds that one can have. For example, there can be beam-induced background, which we can have. Where I was saying we want to keep our beams clean, we want to do all that. We don't always do it perfectly, so we can have some contribution, and that won't scale in the same way. They'll scale a little bit like luminosity, but not necessarily. There are also backgrounds from cosmic rays. Luckily, that one is negligible most of the time. It's only when you do like super weird searches, for example, for long-lived particles, that they become particularly relevant. And we can actually do vetoes to get rid of them. For example, if it's a cosmic ray, it's going to go through the detector both sides, right? And so you can actually look for a track that goes all the way through, and we can use timing information to see that it doesn't happen at the same time as collision. And so the way it really works is we have to, for each particular search, you have to go through and figure out, what are all the different backgrounds that matter, and then deal with them one by one to do it. And so it depends a bit, but yeah, we do worry about them. Neutrinos are generally not a problem. Just because our rate, we have 40 million collisions a second, is way higher, especially since we're bad at detecting neutrinos. So those ones don't cause us much trouble. In fact, for us, neutrinos are mostly invisible, unlike other experiments. Okay, so I was going to say here, sigma is the cross-section. L is the luminosity. Well, I'm not going to define delta T. This is just whatever period of time we're talking about here. And the reason I mention this is that luminosity is actually something we do have to worry about quite a bit to do it. And luminosity is essentially a measure, of how strong the beam is and how many collisions we're going to get, right? So the higher the luminosity, the more events we're going to get. And so that's what we're trying to maximize. Now, luminosity is measured in two different units. One is centimeters to the -2, second to the -1, or much more commonly, we would do it in picobars per second. Now, some of you have seen this before. You might be saying, hold on, why is she saying per second here? Why isn't she just saying, inverse picobars? in general. That's because there are actually two luminosities, and we're generally kind of lazy about distinguishing them. There's the instantaneous luminosity, and there's the integrated luminosity. This one's the instantaneous. And so if you remove the seconds, you just integrated it to get the total luminosity. And unfortunately, although the luminosity matters for everything that I want to do, I have no control. It's determined by accelerator properties. In fact, I will show you how it's determined. So it's going to be the instantaneous luminosity. It's going to be Fn, N1, N2 over 4 pi sigma x, sigma y. And please note I'm using sigma twice, but I'm going to explain what sigma means. Let's start at the back. Could you speak a little louder? Sorry.
I'm just wondering, what do you define as advanced field? Like, for example, at LHC, obviously we say 2 protons collide, produce 3 particles, not the same thing. So what if like 2 protons will glance off each other?
It's a good question, actually. What we mean here is an event would be any interaction between pairs of protons. So indeed, like if we have some sort of soft interaction where the 2 protons scatter, that would be an event. But the sigma, right, the cross-section, would be totally different for that versus the sigma that one would have for example, producing a Higgs boson. Does that sort it out, or you want to say more?
Well, I was thinking like, the way I thought that luminosity is usually referred to is like the total event.
So yes, you can do that, right? So luminosity the question was that luminosity usually refers to the total event rate. The point is that for any process, it will scale with the luminosity to do it. And so we can calculate the total number of events that were produced at all. In that case, we need to use sigma for the total cross-section, which is something we measured at the LHC to do it. So the thing is, luminosity, you can't get away from it. No matter what you're measuring, it always depends on the luminosity. Look a bit confused. Want to ask again? Okay.
Is the instantaneous luminosity referring to like the bunch as a whole, or would that be the integrated luminosity?
Neither. So the question was, is instantaneous luminosity referring to the bunch as the whole, or a single, sorry, what was the second?
I don't know, I guess like a slice of the bunch?
Or a slice of the bunch. So no, instantaneous just refers to time.
Okay.
So it's instantaneous luminosity as in the luminosity per unit time. Total luminosity is over a time period. So for example, we would quote the total luminosity that we had during run 2, right? Which would be 300 picobars of data. Inverse, sorry, to do it. But then the point is, this event, right, in this cross-section is for a single proton-proton interaction, right? But I told you that it's not really one pair of protons that collide. It's typically 40. So we'd actually need to think about, to know how many particles we'd produce, we'd need to think about all those different cross-sections to do it. Any more? All right, so now I'm actually going to define the formula that I put up here. So we've got L equals Fn, N1, N2 over 4 pi sigma x, sigma y. And so here, F is going to be our revolution frequency. And as an example, if we think about the LHC, that's going to be 11 kilohertz. This is simply about how fast are the particles going around, right? Yeah.
All of this is specialized in circular.
This is for colliders. So sorry, I didn't define that. So the question was, is this specific for a circular collider? So yes, these are for a circular collider. You can, of course, calculate the luminosity of a linear collider as well, but it will have a slightly different formula. In particular, it doesn't revolve usually. Then n is going to be the number of bunches. So it's not just about, per bunch. It's how many we put inside our accelerator. To give you an idea, in the LHC, there are 2,808 bunches. Yes.
At a given moment, there's 2,800 bunches?
So the question was, at a given moment, are there 28 and 8? Sorry, I'm not good at 28s and hundreds. 2,808. This is continuous. So the way it works, right, and I'm going to show you a little bit how we inject. We inject them one bunch at a time, but we can continue injecting until we have 2,808, and then we keep them in there while we collide to do it. We don't have to. So sometimes for specialized studies, we might inject fewer bunches, and then we'd have larger spaces between them. But this is the maximum that we can put in the LHC. And if you calculate it, if you know the circumference of the LHC, it means it's about 30 centimeters per bunch. So it's actually not that far in terms of the spacing. And so that's back to your question. You asked about weird backgrounds. One of the really weird backgrounds you can have are parasitic collisions. And what that is when the next bunch happens to collide and might produce particles that interfere with your original bunch to do it. But we get around that by the angles of the beams. So the rate of that is very low. So I have number of bunches. Then big N is going to be number of particles per bunch. And then finally, the second sigma, confusingly enough, sorry, that's the 10 to the 11, which I already mentioned. The second sigma is going to be the transverse size of the beam. And for the LHC, this is going to be 16 microns. Oops. Huh. I guess I have to get it all the way up. All right. So that's basically it, right? That's what gives you the luminosity. I'll come to you in a sec. The luminosity of the LHC. And what you can actually notice is that many of these are kind of fixed parameters. Once you've designed your accelerator, these things are fixed. The thing where a lot of the work goes into is really that transverse size of the beam. And that's something which you can use to increase the luminosity. Question at the back. So the question was if the number of particles per bunch is generic or just for the LHC. This is for the LHC. So it's a choice that can be made, and it's a mixture of different things. So it depends a little bit on your injectors that you have, how many particles you can get in the bunch. It also depends on the quality of the magnets that you have. If you have too many, you'll start getting horrible dispersion and all sort of beam effects that would cause problems. At the LHC, sometimes we have less. Sometimes we inject, we can do injection bunches or smaller bunches than that to do it. But you can see that your luminosity will fall off pretty catastrophically, right? If you did 10 to the 10, that's an order of magnitude less luminosity. That's just going to be far less than you have to do it. But there are a lot of effects that go into that. Good. Okay. Yes?
I'm a little confused why there is N in the form of luminosity, because it is one bunch colliding at a time, or all of them are colliding?
So good point. I didn't explain that. So the question was, why is there N in there? Because is it one bunch colliding or all of them? So you're right that it's always one bunch that's colliding at a time, okay? However, if you think about it, imagine you had an LHC with just 2 bunches, right? What's actually going to happen is you're going to have one collision, then you have to wait for the bunches to go all the way around until they meet up again, and then a collision again. So if you average that over the full time period, right, it's going to be much lower than if you have them continuously. And so that's why it's your luminosity per unit time. And so it's a constant. It's not just at the particular moment when that bunch happens to be in the right configuration. And yes, by the way, when you have just 2 bunches, you have to put them in carefully, right? Because otherwise they might not line up, right, when it goes around to do it. Question there?
I might touch on this maybe later, but I wanted to know if there's some protocol if the bunch is kind of empty, because I imagine there's scattering and there will be particles, and then you might have a bunch that only has like half of the particles left. Is there some protocol to remove them, or what's happening?
Yeah, so I will come to that, some of that a little bit later, but I can answer it a bit now. So basically, if you look at the luminosity as a function of time, once we start colliding, luminosity falls off. And it's for exactly that reason. Particles get used up in collisions to do that. We don't have any procedure for fixing that, right? You could imagine like, you re-inject in one bunch or something like that. The trouble is the way that it really works is you inject and then you accelerate. So you wouldn't be able to do that because they're already accelerated. And so we just don't have the mechanism to do that. So really what happens is that after a while, we decide to dump the beam. So we dump the beam, we start over to do it. There is a little bit of a detail. There's something called luminosity leveling, which is something they haven't really used so far, but they might start using soon. This actually gives you a flatter profile as a function of time, but at the cost of decreasing your luminosity initially to do it. So it's not really doing what you were saying, but it's one thing that can kind of help. Yeah?
So, why can't you just have one very large lump? Is it limited by how much particles you can inject?
So why can't you just have one really big bunch? Because you do worse, is the honest answer, right? Because then you have to wait for that whole big bunch to go all the way around the accelerator to collide again, to do it.
But you have more particles.
But we're limited in terms of the number of particles as well to do it. So essentially what we actually do is we maximize all of these as much as we can without losing something else. Because for example, if you put too many, you'll start getting the particles interacting with each other. So you'd increase the transverse size. And you start losing your beam to do it. So it's an optimization problem, and essentially you try to optimize all of these. By the way, luminosity is a really big deal. It kind of limits almost entirely the physics that we can do. So the higher luminosity, the more physics we can do, and that's actually why I wanted to call it out here. Later on, I'm going to talk a little bit, probably not today, about how we would actually go and measure it, because that also matters to do it. So that was about types of accelerator, number 1, fixed target versus collider. Second one, and this we had a question on, what particles do you put in? Right? So this is lepton versus hadron. Now here, do a simple little sketch. We have an E plus and we have an E minus collider. If we don't have it, the LHC. What we have here is we have 2 point-like particles colliding, or as best we know. And what that actually means is that all the energy is in the collision. So that's great. Trying to get to high energy, let's use as much energy as we can. Another thing is, if you think about this, if you just have an electron and a positron, you're going to be able to study the electroweak interaction. Because that's the only interaction those ones feel. Type number 2, and now I'm going to draw you a funny sketch of a proton. Here are my 3 valence quarks. But of course, that's not everything that's going on. whole bunch of gluons, a whole bunch of C quarks, etc. Can draw proton number 2, should be about the same. Kind of messy object. And this means we're actually colliding two composite particles. Composite particles. I know that's might feel a bit weird thinking about it that way, right? Normally we think about a proton, just two up quarks and a down quark. But indeed, once we get to higher energies, it's actually far more messy than that. And indeed, at the LHC, it's mostly gluons inside the proton that actually collide, not the valence quarks.
Theoretically speaking, if we could pump the E plus E minus stuff to super high energies, could we become, like with all collider kind of physics in mind, could we become sensitive to QCD stuff through loops?
So, I mean, yes, you can always make more complex interactions. The question was, if we could have like a super high energy electron-positron machine, could we get sensitivity to QCD through loops and things like that? Eventually, yes, right, depending on what particles you can produce. But of course, the usual game is to try and produce those particles with a smaller effort as possible, right, to get there. And so you'll have very, very low sensitivity compared to protons. But you know what I'm going to write, actually. So 2 facts. What this actually means is only a fraction of energy is used in the collision. So that's one of the annoying features, right? Because if you looked at the formula that I gave you before, you'd say, we have an LHC with 2 beams of 7 TeV proton. Why aren't we probing things in, the multi-TeV range? The reason is that it's not actually the protons that collide. It's some parton within them, typically a gluon. And what actually controls this are the parton distribution functions. And what's kind of awful in some sense about parton distribution functions is these get really into the messy pieces of QCD, right? Such that we actually end up needing to measure these to actually know the distribution. It's the momentum distribution of the particles that we have. And of course, this can do electroweak plus strong. To do it. All right. I have a spare board. Fantastic. Yeah, question.
Why are we using a plus minus and not just 2 electrons for that? Because in principle, I could do the same thing and just replace the protons with electrons, right? And then never circular ladder and only have one species.
So I'm going to come to circular to do it. So the E plus E minus, it's very easy to produce positrons. And they behave very similarly to electron. So that's typically why it's E plus E minus. That also gives us a neutral charge interaction, which is ideal for producing new particles. If you have an imbalance, that will actually get reflected through in the collision. So that's why it's E plus E minus. As for why we don't do circular, I'll come back to that in a sec to do it. There's a good reason, unfortunately, because yes, you're right. From this, it says we should just do E plus E minus. Yeah.
So I know there's interest in potentially doing a muon collider in the future. What could that buy you that?
I'm going to come back to that. So the question was about muon colliders. It's going to be a similar reason to why electrons we can't do to do it. Okay. Okay. Quick comment about particle sources. And by the way, the reason I tell you this is I still remember the story of like one theory grad student I knew who failed their defense. They didn't know where the electrons came from in them. So I think it's important to actually know these things, when we actually get them, where do they come from to do it. So protons, we have a high E field to ionize hydrogen. And here I have a fun story. So this was before the LHC. It was a previous collider, which is the SPS. So people were, taking data and things like that. And for some reason, it just stopped, right? They just weren't getting any more data. So then they went back in the chain, because there's a chain of accelerators, right? The previous accelerator, what's going on? Can't see. Previous accelerator, what's going on? And eventually, after a while, they realized they'd actually run out of hydrogen in the source. The reason why that didn't occur to anybody is that the number that you use is unbelievably tiny, right? It's Avogadro's number to get you number, and we're talking, 10 to 11 per bunch, far, far smaller. So it's something where you have this little bottle, it's really like a little bottle, and you change, every 7 years or something like that. So no one thought that could possibly be the problem. Then electrons. What we do here is we heat metal to spit off electrons. Then antiprotons is what we used to have in the Tevatron, but we don't in the LHC, essentially because antiprotons are a lot harder to handle than protons. We actually need to shoot protons at target material. And then we need to filter out the antiprotons. Okay. So that's how you'd make the various different particles. And you do have to worry about that, right? You can't just say, I want to buy a box of protons and use them. You actually have to make them yourself, essentially in situ. Now to answer the question that's come up a couple times, which is about number 3, linear versus circular.
I have a quick question.
Yeah, go for it.
About the antiprotons. How does that filtration work? Is it just like charge splitting?
It's charge splitting that you want to do, again, using different magnetic fields to filter them out to do it. So essentially what you can think about, right, is you can filter to go different directions depending on the charge, right? And you can also filter depending on the mass. And so you can essentially just accept through whichever ones you want. So that's a typical technique you'd use. Yeah.
Can you describe a little bit more about how do we get antiprotons? Like what material is energy materials
The antiprotons, so this I have to check for you. So the question was, what material do we use for antiprotons? This I'd have to double check for you. This I don't know, actually, but good question. Similar technique as electrons. The thing is, right, with electrons and positrons, they're really similar particles, whereas an antiproton, right, we have a whole bunch of matter around, and so they're much harder to handle to do. I believe so. I can double check for you to be absolutely sure to do it. Okay. So linear versus circular. Draw nice little pictures that we have. So this comes to a whole bunch of questions about electrons and circular machines. One of the main advantages, first of all, is if you have a circular machine, you can reuse your magnets and your accelerating structures many times, right? So you inject your particles into your ring, they can go around, and they can circulate and get accelerated. And so that saves you tons of money. In a linear accelerator, most of the time, not exclusively, there are some techniques where you can reuse them. You can go through the accelerator just once and collide. And so that means that if you want to accelerate things, you have to make it bigger and bigger, which gets more expensive to do it. Yeah. So this is just something I came across to look at. And I didn't read enough on the details of how one would actually reuse it. Because, well, what I'm going to talk about in a second, synchrotron radiation, is going to be a concern. And so I didn't manage to find enough detail to see exactly how much they could do with that. I believe it's mostly in the injector stage, from what I was seeing. Okay, and so then one of the main problems that we have is something called synchrotron radiation. And that's, of course, something you've seen, right, in various different electromagnetism courses. And what it's controlled by is the Larmor formula, which is simply the power. It's going to be 1 over 6 pi epsilon naught E squared A squared C cubed gamma to the 4, right? And this is simply if you have a particle, charged particle, which is accelerating, right? And so if we're going around a circle, we're absolutely accelerating, we're going to radiate, right? And there's not much we can do about that. That's just basic electromagnetism. And more or less, ends up being proportional to something like m to the 4, right, in terms of the dependence. And so, actually, let me put it here. What that means is that if you calculate it for electrons, you get something like 8.85 times 10 to the minus, the units are going to matter here, minus 5, e to the 4 over rho MeV per turn. This rho here, that's going to be your curvature of your accelerator, right? So the bigger you can make it, or the smaller you can make it, it's going to change rho. And so that one is for electrons. Whereas for protons, it's going to be 7.8 times 10 to the minus 3 E4 over rho. And that's only going to be keV per turn. And this is essentially the big problem with electrons, right? So this is kind of trying to answer all your questions about it, is that if you put electrons in a circular collider, because the electron mass is so much less than the proton mass, you essentially are limited in the energy you can get to because those electrons start radiating away due to all their energy to do it. Yeah?
I'm confused about how you get the m to the 4th factor because there's no mass in this.
Yeah, so it comes out if you dig into the gammas, I think, to do it.
Is gamma just the
Yeah, but you got to put in the velocity, right? So you got to convert from the momentum to the velocity. So I think it comes out through that to do it. But it's a good question. Yeah.
You said rho was the curvature of the accelerator. When you say curvature, do you mean rho 1 over r, or is it r?
It's going to be because essentially, right, as you make the accelerator bigger, right, which would be increasing the radius, the power is going to be less to do it, right? So that's one way to get around it. That's actually one of the reasons why we want to build gigantic accelerators, is you can reduce the amount of radiation.
So rho is radius, right?
Yeah, exactly, to do it. And that goes to the question I think you were asking about muon colliders. So one of the advantages of a muon collider, right, is a muon is way heavier than an electron. And so we don't have as much of a problem with synchrotron radiation that we would have with electrons to do it. And so that's one of the reasons why it's attractive, because it gives you the elementary particle, right? So we get all the energy. It's heavier, so it radiates a lot less to do it. However, muons are really tricky. And the muon collider is actually not a particularly new idea. It's in fact something that people have been working on for a long time. The main trouble, in fact, is that muons have a very short lifetime. And so being able to produce your muons, right, and accelerate them up and do all that before they decay is troublesome. Secondly, even producing a beam of muons is actually hard to do it. And so actually getting them produced with a uniform momentum or energy distribution is another challenge that they have. And so they've been sort of decade-long experiments trying to prove this. So I'm kind of torn on muons, if you ask me my opinion. I think it's a cool idea. It's kind of fun. I'm not yet convinced it's necessarily going to work to do it. There are other people who tell you, yes, it's definitely going to work. So that's just my personal opinion about it to do it. And so those are some of the things that get discussed. How are we doing on time? We've got 5 minutes. Actually, let me see if there are questions. I was about to tell you a whole bunch about the LHC. Yeah?
You mentioned some time ago you dumped the beam from an LHC after. Does that make it a beam dump experiment?
So yes, that's a good point. So in the LHC, what we have is so the question was, how do we dump the beam in the LHC? So in the LHC, there are actually 8 points where the beams could collide. Okay. And we'll talk a little bit tomorrow about the different experiments that we have. One of those places is a beam dump. Okay. And the problem is you have to get rid of all that energy in some way. And so the way that we do it is that our beam dumps is we have huge chunks of metal, right? And we fire the beam at it. And so that's basically what a beam dump is. Now, you have no choice. You have to dump your beam, right? Otherwise, it's going to bore holes in the rock if you just ignored it to do it. And that can provide you with an opportunity for doing beam dump experiments. These are simply experiments that are done at the beam dumps to study various things. I'm not super aware that we do too many at the LHC. I might be wrong. So if you know some, do correct me. But people do look at that as an attractive thing. By the way, that is the most radioactive place of the whole LHC by far, the beam dump. And that stays radioactive for a very long time. Other questions? Yeah.
Is there an active way of measuring all these parameters in spot, number of particles? Let's see, and if there is, does that make losing particles and less efficiency? How does that work?
So the question is, can we measure all these different parameters at the LHC?
Effectively, I mean, making sure that they are really what we expect.
Yeah, making sure that they really are what we expect. So yes. So here we have many beam monitors throughout the LHC, which will measure many different things. The bunches, that's the easiest one, because we can actually see, right, as they go by, we can see if there are bunches in there. We also measure the luminosity. We keep an eye on the luminosity. And so we would notice, for example, if there's a significant drop in luminosity bunch to bunch, that would indicate typically some problem. Because remember, the number of particles per bunch is 10 to 11. We have 40, right, in a collision. 40 is not going to change 10 to the 11, right? It's going to take, you have to have many asymmetric collisions to get a big difference. The one we watch the most, I would say, is the transverse size. Because what happens is, when we initially inject, the beam is a bit fatter. And then when we're getting ready to collide, we squeeze it. So we make it smaller and smaller. And there you can actually watch on the display as they're doing it. You can actually see the size that we would actually have to do it. So
what kind of watching this? What is that kind of detection?
So what kind of detectors? You're getting to the end of my knowledge. We'll have to go and check that out. I believe some of it is their collimators. But I think in the end, essentially, most of what they're doing is they're just looking to see, for example, to measure the size, right? You just put something at a fixed distance, and you check if any particles hit it. So that's my understanding to first order, but we'd have to dig in and have a look to see what they are. Yeah? The E or the epsilon?
I don't know is it a E? Sorry, the MEV person. There's something.
This one. Sorry, bad writing. So the question was, what's that? That's energy.
And the rho is the density.
No, the rho is the curvature, which we were discussing about. So it's essentially related to the size. And so these are just different things you could do to decrease it.
It's just one of the radius
of the accelerator. Yeah, it sounds easy, right? I mean, it's a formula, 1 of the radius, but like doubling the size of your accelerator, that's like doubling the cost to do it.
Aren't they like more than one numbers?
Okay, you're definitely a theorist.
No, I cannot visualize how many MAV we lose per turn. To the LHC.
No, so the LHC is not order 1. The LHC is 27,000 kilometers.
But like, what are the units for the ease and load? I guess the way to ask is like, if you accelerate the electron, how many times before you lose half its energy?
No, so it's absolutely impossible to put electrons in at the LHC. You would lose it. No, so sorry. Okay, so your question is how much energy do we lose at the LHC like this?
More like, do we have like, well, what kind of units are we using for it?
So we're using typical particle physics units. So we'll be using MEV or GeV. I mean, it's just written out there in MEV and keV to do it. But no, it's not order 1 at all. And so the point is that the point I'm trying to make is, in fact, there's a critical energy that one has for electrons, such that if you try to accelerate your electrons beyond that, you essentially lose all your energy right away to do it. And so that's why electrons and positrons, they're limited in a circular collider to how high energy they can do. You can sort of see this a little bit if you look into like the FCCEE proposals, right? Like these are, and you put electrons in the LHC and see how high. You'll notice that they don't go to super high energy. In particular, like they can't access the Higgs self-coupling with that. And this is because of synchrotron radiation, you're really limited effectively in the energy that you can do for a collider. Time for one more, or should we wrap up? Last one, yeah.
I just have a question on the outlook of this plasma Wakefield. You mentioned these shorter distances, but I'm wondering on like what kinds of energies or luminosities can we hope for?
So I don't think we know yet, okay? So at the moment, they're all kind of demonstrated tabletop things. And so they can get, like on this sort of scale, I forgot the number exactly, but they can get really fantastic energy gradients. But where they've struggled is to make it any bigger. And so the problem is to answer that question, right, if it can't be made bigger, then we don't know to do it. So it's really, this is still in sort of accelerator R&D. And so like at recent discussions of, when this might be, it's on the order of decades still.
Really?
Yeah. No, I'd love it. If we could do that tomorrow, right? Then we could we can go build an accelerator in the basement and save ourselves tons of money. All right, thank you, everybody. Hi.
I just wanted to introduce myself.
Sure.
I'm Anne Catherine.
Hi, Anne Catherine.
Nice to meet you. Thank you so much for answering